How's everybody doing today? Today we will investigate the experiment number 8 in Labflow, which is determination of the molar mass of an unknown diprotic acid and the identity of the unknown acid. Last week, if you remember, you performed a titration of acetic acid with sodium hydroxide, and you used phenolphthalein to determine the end point. You remember that the indicator turned pink at the end point. In today's experiment, we will also do an acid-base titration, but we will use a pH meter instead of an indicator that will allow us to track the change in pH as we add titrant, as we add the base, and we will track the pH about each milliliter of adding base. And then we will construct a pH curve, which is the plot of the pH versus the volume added of the base. And from the curve, we will determine the 2 ionization constant because it's a diprotic acid. So we will determine from the curve the Ka1 and the Ka2. And also we will calculate the molar mass of the unknown, and from a table that is given, you will determine which one is your acid. So as we always do, each week I will give you a quick overview of the experiment, then we will go over a learning check, and towards the end we will look at the report and make sure you have all the elements to complete your report. So let's get started by sharing the page of the experiment. Okay, so here we have a little introduction page, as they always give us a little background of the experiment. And in the introduction page showing us that not all acids, only one acidic proton to titrate. So here is similar, but this is a strong acid, but it's monoprotic. It has only one acidic proton. And we, in this case, we have 1 mole in this reaction. 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid. But in today's experiment, we will have 2 acidic protons. Here is showing an example of sulfuric acid. Sulfuric acid has 2 acidic protons. So which means that 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. And in general, because we don't know the identity of the unknown, we can write our unknown like that. H2A, in general, is our unknown diprotic acid. And because it's a diprotic acid, you know at this point that it will have 2 ionization constants, Ka1 and Ka2. So which one is Ka1? Well, first they are giving us the K for just a monoprotic acid. We already seen that, and the expression is the same as we've been studying this in equilibrium. So this is the expression of the ionization constant for a monoprotic acid. But what happens if we have this one? We have, well, how is the expression? That's why we are going to have 2 ionization constants. the first ionization constant is related to, let me see if they write it here. Okay, so this is what happens. We have a diprotic acid, and it's going to release only one proton at a time. So the first proton, this is the expression. When it releases just one proton, so from H to A, you just subtract one proton and you write this expression. And this is the expression of Ka1. And once you have the acid with just one, okay, then the Ka2 is associated with a second ionization reaction. Any questions so far? This is kind of straightforward. This is the expression of K1, and this is the expression of K2. And we will construct a titration curve because we have a pH meter. And you know, unfortunately, you can go to the lab and work with pH meter, but basically, it measures the pH of solutions. It's an electrode that reads the voltage of the solution, and the voltage is related to the concentration of protons. The good part of the pH meter is that you can track the pH at each addition. When you watch the videos, you will see that you have to calibrate the pH meters using buffers to make sure that when you read a solution, you read the proper pH. And then what is telling us here in the introduction, that we are going to construct a curve. The first example, so this is, we are going to do a titration curve. That is a plot of the pH, as we just said, versus the volume of titrant added. And here is how it looks, the curve for a monoprotic acid. You see that it has an S shape, and it has only one inflection point because it's monoprotic. And the inflection point, as is written here, is the equivalence point. Remember, what is the equivalence point? Is when the number of moles of the base is stoichiometrically equal to the number of moles of acid. This is key so you understand. Is at this point, when you are at the end point, you don't have excess. No excess of neither of the reactants. So this is just important concept to see. This is here. And then what else is showing us in this graph? This is for a monoprotic acid, and it's easy to recognize because it has only one inflection point. And then it's showing us that if we divide the volume of sodium hydroxide to reach the equivalence, which will be this one, by 2, the volume is this one, is half, is called half equivalence point. The name is clear, I mean, it's half the equivalence point, there is nothing new. But why it's important, the half equivalence point? Can you tell me? Can somebody tell me why it's important to get the half equivalence point? It is very important because at that point, the concentration of the acid, equals the concentration of the conjugate base. And if you look at the equilibrium constant, at the expression here of the equilibrium constant, if the concentration of HA equals the concentration of the conjugate base, we end up that the Ka equals the concentration of protons. So that's how we are going to determine the Ka of the acid from the titration curve. Any questions so far? So if we move forward, you are going to see what we have just seen, that at the half equivalence point, the pKa equals the pK. So the Ka of a weak acid can be determined from the titration curve from the acid. This is what we are going to do today. And then for a diprotic acid, the titration curve will have two connected shapes. Instead of one, it has two connected S shapes. So the acidic protons are removed one at a time and will give us two equivalence points. One is here and the other is here, right there and right there. So the first inflection point, which is this one, is where the first acidic proton is removed. And the second is when the second acidic proton is removed. And the second volume should be 2 times the volume of the first equivalent point. That makes sense. And then what else is telling us in the introduction? It's telling us that we will have the grams of the unknown, and we can calculate using the second equivalence point. We can calculate the number. Basically, it's showing here how are we going to calculate the molar mass. And that is really, really easy because it's a diprotic acid. So the initial moles, if you use second equivalence point, is the moles of sodium hydroxide divided by 2. And then the molar mass, obviously, is going to be the weight divided by the number of moles. Any questions so far before we move to the learning check? Okay. What is a titration curve? And how you determine the equivalence point? Okay, this is an easy question. A titration curve is the plot of the volume of titrant versus the pH. This is what we are going to work today. And how to find it? The equivalence point. Just finding the steepest slope in the curve. We saw that, we saw how the graphs are, and we saw that it has kind of something like that. So the steepest part of the steepest slope in the curve, we are going to find the equivalence point. Does it make sense? Okay. Okay. Let's go at the second one. Let's read the problem. We have a monoprotic acid. We have the mass of the monoprotic acid. And they tell us that they are titrating the monoprotic acid with this volume of base, and they give us the concentration, and they ask us for the molar mass. That is obviously very, very simple and straightforward. What is the molar mass? From Chem 1 is obviously the grams divided by the number of moles, right? How many grams we have? 0. We weight the monoprotic acid, and we have these grams. What is the number of moles? The number of moles, because it's a monoprotic acid, 1 mole of acid reacts with 1 mole of base. So it will be the same as the number of moles of the sodium hydroxide. And what are the number of moles of sodium hydroxide? Volume times concentration. As long as we write the volume in liters, we are safe. Times the concentration that they are giving us, that is 0.510 mole. Moles per liter. This cancels with this, and we are going to obtain a number. I think I got 65 if you do this calculation. Any question with this kind of problems?
I have a question. Hello?
I can hear you.
If it was a diprotic acid, would you have to divide the concentration times the volume and then divide that by 2?
Basically, if you have a diprotic acid, in here, you are going to say, if you look at this reaction, let's say you have H in general that reacts with sodium hydroxide and forms, you need how many, you are going to form a salt plus let me put it in general. Let me write it correctly. Let me find it. We can do, let me find, I'm looking for something that I don't see. That's okay. Okay, so let me erase it and write again, because this is important. This is important. So if you have, let's say, a diprotic acid, right? Let's say you have sulfuric acid that reacts with sodium hydroxide. What are the products? Sodium sulfate plus water. When I balance the equation, which is important, what is important is that here I have a 2, right? when I balance the equation. So you are going to calculate first the number of moles of sodium hydroxide, right? Number of moles of sodium hydroxide is going to be the volume of the sodium hydroxide that you use in liters, like we just did, times the concentration of sodium hydroxide. But you are not interested in the number of moles of sodium hydroxide. You are interested in the number of moles of sulfuric acid. So the number of moles of sulfuric acid is going to be the number. How do we relate these two? With a molar ratio. It's going to be the number of moles of sodium hydroxide, and then we use the molar ratio. We know that 1 mole of sodium hydroxide reacts with 2 moles of sodium hydroxide. So the number of moles of sulfuric acid is going to be, as you said, the sodium hydroxide divided by 2. But if you have a triprotic acid, the ratio is different. Did I answer your question? Okay, great. Then we are going to move into this. Determine if the acid is a strong or weak acid. How about A? Is it a strong or a weak acid? Yes. How about the second one? Strong, very good. And how about the last one? Citric, weak acid. So what are you looking at? You know that if the pKa is lower than 1, it's going to be exactly whether the number is greater than 1. Exactly. It's a strong acid. Perfect, Kevin. Yes. And if we have a weak acid, usually the pKa usually will be between 1 and 7. But yes, very good. So let's move into the next one. And here it says, how is the pH at equivalence point when titrating the following solutions? So this is important to understand. Let's look at the first one. When you reach the equivalence point, you know stoichiometrically number of moles, there is no excess of hydrochloric acid reacted with ammonia. But what you don't know is the pH. Can you figure it out if this is going to be acidic or basic or neutral? Hydrochloric acid is a strong acid, and ammonia is a weak base. So when a strong acid is titrated with a weak base, like in our case, that is ammonia, the equivalence point is at an acidic pH. Why is that? Because the conjugate acid of the ammonia has acid character. So this is a strong acid. so it's not going to change the pH. But what happened with ammonia? Ammonia reacts. So we have the does it make sense what I'm saying or not? What I'm trying to tell you is let's start in a different way. I want to make sure that it's clear why when you titrate a strong acid with a weak base, why is going to be a pH acidic. We said that the conjugate acid, the weak base, has acidic character, and that's why the pH is going to be acidic. So we know that there is an equilibrium, right? And the conjugate base, the conjugate acid of ammonia is ammonium. And it's in equilibrium with ammonia and a proton. That's why this makes it more acidic. Does it make sense? Some people remember, okay, if I have a strong acid and a weak base, the pH at the equivalence point will be acidic. But I wanted to show you that because the ammonia is a weak base, is going to have the ammonia is going to react with water and it's going to be an equilibrium to form ammonium plus OH. But this reaction is not going to happen. I don't know if I'm confusing you. When hydrochloric acid reacts with ammonia, the titration is going to produce ammonia plus chloride. This is what happens in the titration. And then I think this is going to be an easier explanation. This is the titration reaction of hydrochloric acid and ammonia to produce this. But this, because it's the conjugate acid of a weak base, is going to release more protons. And that's why the pH is going to be acidic. Any questions there? Okay, let's look at how is going to be the pH. We know it's a titration. So nitric acid is going to react with potassium hydroxide. And we are going to have potassium nitrate plus water. And then this is aqueous. And we are going to have potassium that comes from a strong base and nitrate that comes from a strong acid. So what would be the pH in B? Okay, you said basic. Neutral, yes. Stream, you got it. Kevin, Okay, so let's go over again because this actually is very confusing, very confusing. So let's look at it. Why is it neutral? Because these are spectators. It comes, so this is going to be neutral, the B. Why is going to be neutral? When a strong acid is titrated with a strong base, which is what we have here, the equivalent point is neutral because none of the species has acid or base character. So none of these, potassium, this one is a strong acid and this is a strong base. The pH at the equivalence point, it will be neutral. In the first case, you have a strong acid that reacts with a weak base to form ammonium and chloride. But the ammonium, because it comes from a weak base, is going to release some protons, making the solution more acidic. But only if you come from a weak acid or a weak base. Let's look at C. We have this reaction. We have a titration, right? So we have acetic acid that reacts with sodium hydroxide. It's a titration. And what do we have? We have the salt plus water. We can write this as sodium plus because it's aqueous, and we can write the acetate ion. Sodium comes from a strong base. So that is something that will be important for you to learn. Which one are the strong acids? Memorize those. There are only 6. Look at which one are strong bases. Usually group 1 and some of the group 2. Sodium hydroxide, this comes from a strong base. If it comes from a strong base or a strong acid, it won't be a hydrolysis. But this one, which is the conjugate base of the acetic acid, is a weak acid. So it's going to react with water to form more acid plus OH minus. If you see the hydroxide group, means that it makes the solution more basic. So this is kind of the reason. If you want to remember just remember. You can also remember when a weak acid is titrated with a strong base, the equivalence point is at a basic pH. Why? Because the conjugate base, which is this one, of a weak acid has basic character. What does it mean, basic character? That it will release OH, in this case, that is basic. Any questions on this explanation? Okay, so then we'll go to the next one, and this is easy. What is the Ka of an acid if the pH at half titration is 4.2? That is what you are going to do in your report. You know that the pH at the half titration, yes, thank you, awesome, exactly. So Ka is going to be 10 raised to the minus 4.2. And that's okay, I obtained 6.3 times 10 to the minus 5. Any questions before we go to the report and make sure you are ready to complete your report? So you will be given the data of the pH at each different volume. So actually the calculations are really simple in this that's what I think. So you are given this, all the data in red, you are giving all that data. The first thing they say, you're going to have a titration curve. I believe it's coming up automatically. I have by Excel, I did it also with this data, I put it in Excel. But you know how the, let me see if I can share the, let me see if I can share the Excel data. No, it looks like Excel cannot share, but I can share as an application. That's okay. I want to make sure that the first thing that is going to ask is identify the second equivalent point. So let me look at, let me share the Excel. Okay, so when I plugged the data in Excel, I obtained this curve. We already seen at the beginning, it's like 2S shapes. And they will ask you, here it says, use the titration curve to determine the equivalence points for the unknown. The volumes at 50%. And that it will be Ka1 and Ka2. So the first part, it says, identify the second equivalence point in the titration curve. Use the two volumes measurements where the largest change in the pH occur. So we know that if they are starting here in this part, we know that this is the steepest slope and it's going to be the second equivalence point is going to be over there. So what we do is to look at where is that happening. So we look at the data, and when I look at the data, I see that at 28.03, the pH is 6.95. And when the volume is 29, the pH is, so that I checked, and that is basically the biggest change in pH. And then they actually tell you very clearly that take the average of these two volumes, and that will be your equivalence point. So that it will be easy to find. And then they ask you to identify the first equivalence point. And that is at half of the volume of whatever you recorded. So basically, they're telling you step by step how to do it. That's why I think the concepts in these experiments are a little confusing. But what you have to do. Okay, Kevin says, how do you take the average of the two volumes? Well, you add and divide by 2, right? That's how you take an average. You take the two volumes that you see, the biggest change in pH, you add those two volumes and divide by 2. And then I guess you will have to calculate the first equivalent point. It will be half of what you already calculated. But then they say, look for the large pH change near this value. So if you follow all these, it's very, very simple. And then the 50% of the first equivalent point, you basically divide by 2. So I don't see many difficulties. It's time consuming because you have to obtain the titration curve. But then from the curve, you are going to obtain Ka1, the Ka2, and it's straightforward. That's how I'm seeing it. Any questions there? Okay. So, any question with understanding the titration curve? So this part should be simple. And then in part B, you will have to calculate the molar mass of the unknown. How are we going to do that? The first part, moles of sodium hydroxide needed to reach the second equivalence point. So we know that the number of moles of our diprotic acid, so the number of moles of the diprotic acid, we said that it's going to be, because it's diprotic, the number of moles of sodium hydroxide divided by 2. And the number of moles of sodium hydroxide is the volume, but they say use the second equivalent point. So the volume that you found in the second equivalent point times the concentration of the sodium hydroxide. I believe is 0.5 moles per liter. Then you divide by 2 and you obtain, okay, no, this is, sorry, this is here, goes here, the number of moles of unknown acid. The number of moles of sodium hydroxide is just multiplying the volume times the concentration. And then how are we going, once we have the moles, it's very easy. We know how much we weighted. I think they are telling us, in my case, everyone has different data. 0.75 grams divided by the number of moles that you calculated here. So I think this, it feels to me that is straightforward. And that's how you calculate the molar mass. Grams per number of moles. And then once you have the value of Ka1, Ka2, and the formula, no, not the formula, the molar mass, well, they give you the formula. You are going to use that formula to calculate the molar mass. And then once you have the molar mass, you'll compare the molar mass with the one that you have. And you will guess which acid do you have. Any questions on how to do the report? The next part, I will ask you which one is the most likely. And that is only by comparing that data that you obtained. But I will wait till after the meeting is done recording. Okay, so I will stop recording and I will stay in case you have questions. I will be happy to answer them.